You are about to step into a mystery where science meets the unknown. Imagine the cosmos as a vast stage lit by a single, patient spotlight. On that stage, every atom, every star, every life form performs a dance, choreographed by numbers. Quiet, invisible numbers that never change their steps. The tiniest tweak to those numbers and the play ends before it begins. Gravity loosens its grip and galaxies never form. The strong nuclear force weakens, and the periodic table collapses to a barren handful of elements. The cosmological constant swells and space expands so quickly that matter never settles into anything more complex than a diffuse mist. Yet none of that happened. Our universe balanced its equations with improbable precision, and here we are. Telling stories, asking questions, looking back at the numbers and wondering whether we've been the beneficiaries of a cosmic coincidence, a natural selection among universes, or something more profound. And if you'd like to help me bring more of these mysteries to life, don't forget to like, comment, and subscribe. Tonight we follow the trail of a puzzle that begins with a simple observation and ends with the most audacious ideas in science. Why do the laws of physics seem so precisely adjusted for life? And what might that tell us about reality itself? Stay with me, because the heart of the mystery is not just whether the universe is fine-tuned. It's why there is a tuning at all. The awareness that our universe is balanced on a knife's edge did not arrive in a single flash of insight. It crept in, decade by decade, as scientists learned to read the universe's instruction manual. Early clues came from nuclear astrophysics in the mid-20th century, when researchers asked how stars forge heavy elements. They discovered that carbon, the backbone of biochemistry, forms in stars through a delicate, multi-step resonance. If the energy levels in atomic nuclei had been arranged just a little differently, the efficient production of carbon and oxygen would have faltered. Later, cosmologists mapped the faint afterglow of the Big Bang, the cosmic microwave background, and saw that the early universe came seeded with tiny ripples in density. Tiny, but not too tiny. The amplitude of those ripples, roughly 1 part in 100,000, was just right to grow into galaxies without collapsing into black holes en masse. Meanwhile, particle physicists, pushing deeper into the subatomic world, realized that the values of certain constants, couplings, and masses that live in the standard model had to sit inside narrow windows for atoms, chemistry, and stars to persist for billions of years. Consider the fine structure constant, that dimensionless number about 1 over 137 that calibrates how strongly light couples to charged particles. If you treat it like a dial and turn it significantly, stable atoms become scarce, chemical bonds change character, and familiar complexity withers. The history of science is filled with moments like these. Places where a counterfactual twist snaps the ladder of complexity. None of this proved a grand design or a multiplicity of universes. It simply raised the temperature of a question. Why are the knobs where they are? By the 1970s, the puzzle acquired a name. Physicists began to speak openly about anthropic reasoning. Not because humans were central to the cosmos, but because observers like us can only arise in certain kinds of universes, and that selection bias colors everything we see. At first, anthropic talk made many scientists uneasy. It seemed to flirt with circular reasoning. We observe a life-friendly universe,
because only in a life-friendly universe could anyone be around to observe it. True, but not the end of the story. That tautology becomes interesting only when paired with a hypothesis about alternatives. If there exist many possible settings for the cosmic dials, whether across time, space, or a broader landscape of possibilities, then it is no surprise that some of those settings permit life. In the 1980s, an intriguing prediction added weight to this line of thought. If the cosmological constant, the energy density of empty space, could vary among hypothetical universes, then observers would most commonly find themselves in a universe where that constant is small but not zero. Large enough that space eventually accelerates, but not so large that galaxies never form. Years later, the discovery that our expansion is indeed accelerating, driven by a tiny but positive vacuum energy, seemed eerily consistent with that reasoning. It didn't prove the existence of other universes. It simply showed that anthropic arguments can sometimes be testable in flavor, if not in finality.
What exactly is being tuned? At heart, fine-tuning is about the sensitivity of complex outcomes to small changes in fundamental inputs. Think of a mixing board in a recording studio. Each slider controls a different parameter of sound: bass, treble, reverb, gain. Slide them arbitrarily, and the audio turns into noise. But in the hands of a skilled engineer, the sliders find a narrow corridor of settings where a symphony emerges. In physics, the sliders are dimensionless constants in initial conditions: the strength of gravity relative to electromagnetism, the ratios of particle masses, the couplings of the strong and weak nuclear forces, the amplitude of primordial fluctuations, the density of dark matter, the value of the cosmological constant, and more. Some of these numbers are built into the structure of our theories as free parameters, values we must measure rather than derive. Others describe the early universe's state at the moment physics first becomes classical enough to talk about it. When we simulate nearby universes by nudging these values, we often find that the corridors leading to long-lived stars, diverse chemistry, and planetary habitability can be narrow. Gravity offers a vivid example. Between two protons, the electromagnetic repulsion is about 10 to the 36th power times stronger than gravity's attraction. If gravity were much weaker relative to electromagnetism, matter would have a hard time clumping. If much stronger, stars would be tiny and short-lived, burning their fuel too quickly for life to evolve. The weak nuclear force governs how quickly stars transmute hydrogen into helium through processes that emit neutrinos. Altering its strength too much changes stellar lifetimes and the production of heavy elements. The masses of the up and down quarks, together with the electromagnetic interaction, set the delicate mass difference between neutrons and protons. Protons, around 1.3 mega-electron volts. Shift that difference in the wrong direction, and free hydrogen becomes unstable or neutrons dominate, upending nuclear chemistry. The strong force must be just strong enough to bind two protons and two neutrons into helium, but not so strong that almost all protons get locked away too quickly. Otherwise, hydrogen, crucial for water and organic chemistry, would be scarce. Even the resonance in carbon that helps stars build heavy elements is sensitive. Change the underlying forces enough, and the resonance moves, lowering the yield of carbon and oxygen that planets and biochemistry require. cosmic initial conditions tell a similar story. In the first instant after the Big Bang, however we ultimately define instant in quantum cosmology, the universe possessed an extraordinarily low entropy. A smoothness that seems, by some measures, fantastically unlikely. That smoothness allowed gravity to patiently amplify tiny density seeds into galaxies and clusters, rather than descending immediately into chaos. The amplitude of those seeds imprinted in the microwave background sits in a Goldilocks range. The cosmological constant, meanwhile, is so small in natural units that it looks, to many eyes, absurdly fine-tuned. Roughly 1 part in 10 to the power of 122 compared to the Planck energy density. Why should empty space have an energy that is not exactly zero, yet not catastrophically large? In our best quantum field theories, vacuum fluctuations tend to pile up contributions to this energy, and naive expectations overshoot the observed value by staggering factors. Taming that mismatch, sometimes called the cosmological constant problem, is one of the great technical riddles of modern physics, a place where fine-tuning and deep theory collide. If the problem were only that our universe is special, we might shrug and say, of course it is, for us. But the difficulty is deeper. We do not yet possess a theory that predicts the values of these constants from first principles. The standard model and general relativity tell us how the dials work, not why they read what they read. That means the question, why these numbers, is not just metaphysical musing. It is a concrete, unsolved problem about the origin of parameters in our best theories. In particle physics, this appears as puzzles of naturalness. Why is the Higgs boson's mass near the electroweak scale instead of surging to the Planck scale under quantum corrections? Why are neutrino masses so small? Why do the 3 forces of the standard model nearly, but not exactly, unify at high energies? Solutions have been proposed: supersymmetry, compositeness, extra dimensions, but so far nature has offered no decisive experimental confirmation. Without a mechanism that fixes the numbers, we are left with 3 broad possibilities. The numbers are outputs of a deeper theory we have not found. The numbers vary across a vast cosmic ensemble, and we occupy a habitable patch, or the numbers reflect some selection or purpose that lies outside conventional physics. Each path has promise and pitfalls. Let's walk them one by one. First, inevitability. In this view, there is a unique or highly constrained final theory. Call it a theory of everything, from which the values of the constants fall out as the only consistent solution. There is no freedom to dial them. There is only the correct answer, enforced by mathematical consistency. This would be the most satisfying outcome to many physicists. The universe is not chosen. It is deduced. The barrier here is practical. Our candidate frameworks, quantum gravity programs, unification schemes, have yet to deliver a unique predictive set of parameters that match our world. Even if the final theory exists, it may demand boundary conditions or vacua that reintroduce choice. The dream of inevitability remains alive, but unproven.
Second, multiplicity. Perhaps reality contains a large ensemble of regions, domains, or bubble universes, each realizing different effective laws or parameter values. In some versions, high-energy physics provides a mechanism, a vast landscape of possible vacuum states, each with its own constants, combined with a cosmological process, like eternal inflation, that populates those vacua across an enormous space-time. In that case, most observers will necessarily find themselves in a habitable domain, not because the universe had us in mind, but because observers cannot exist elsewhere. This approach can explain why we measure a small, but non-zero cosmological constant. In most domains, it might be too large for galaxies, so observers arise in the rare, life-permitting pockets. The strengths of this view are its explanatory power for otherwise baffling small numbers and its compatibility with some modern theoretical ideas. Its weaknesses are subtle, but serious. It invites a measure problem. How do you define probabilities in an infinite or vast ensemble? It risks unfalsifiability if other domains are forever beyond observational reach, and it can drift into a catch-all explanation that feels too easy. If everything happens somewhere, what does the theory truly predict? Third, selection or purpose. Across human history, many have interpreted fine-tuning as evidence of design, cosmic teleology, or as a hint that we inhabit a simulation where the tuners are literal programmers. These ideas step beyond the methodological naturalism of physics, but they raise testable-ish questions. Would a designed or simulated universe leave signatures? Some have proposed that a simulation might betray itself through computational shortcuts, limits on resolution, or anomalies in fundamental noise spectra. Others suggest that a designing intelligence could leave a readable message in the fabric of mathematics or the constants themselves. So far, no such signatures are accepted as real. Absence of evidence is not evidence of absence. But it leaves these ideas in the speculative shadows. They carry different challenges. Design begs the further question of the designer's origin, pushing fine-tuning up a level. In simulation, pushes it sideways. If our constants are tuned in software, why do the tuner's constants permit tuners?
Within and around these broad roads, there are side paths worth exploring. Consider cosmic natural selection. In this proposal, universes give birth to new universes through black holes, with constants that vary slightly from parent to child. If true, it could explain why our laws seem optimized for prolific star formation and black hole production, which, incidentally, also seed heavy elements and long-lived stars. It reframes fine-tuning as a Darwinian process at the cosmic scale. Whether the mechanism exists and whether it would truly favor life-friendly constants remain open questions. Another path: law without law. The idea that what we call laws could emerge from deeper statistical or informational principles. Perhaps the constants we see are attractors in a vast space of possibilities, fixed not by design, but by stability and self-consistency. Or perhaps what appears as fine-tuning is just a mirage of poor priors. If we had the right way to assign probabilities over possible constants, guided by the mathematical structure of fields and symmetries, the observed values would land in the middle of the distribution, not at its edge.
There's also the question of how much tuning is truly required for life. When researchers perturb constants in simulations, some windows are surprisingly forgiving. Carbon and oxygen production, for example, can tolerate certain modest variations while still producing usable amounts. The habitability of universes turns out to be a high-dimensional, tangled problem. Change one constant and doom follows. Change several together and the doom can be averted by compensations. The space of life-friendly physics might be larger than early arguments suggested, yet it remains far from generic. Universes filled only with helium. Universes where stars die in minutes. Universes without stable deuterium or carbon. These are easy to generate in thought. The razor's edge may not be a single hairline. It may be a narrow ridge weaving through a mountain range of sterile options.
How could we ever decide among these possibilities? With difficulty, but not impossibility. One strategy is to look for patterns among the numbers we do have. If low energy parameters secretly encode high energy consistency relations, we might eventually see the fingerprints of a deeper theory. Another is to search for signs of a multiverse that bleed into our observable patch. Collisions between cosmic bubbles could, in principle, scar the microwave background with telltale circles or disks. No such scars are confirmed, but the search continues. We can also test the rigidity of the constants themselves. If some values drift over time or vary across space, that points away from a rigid, unique theory and toward dynamical or environmental explanations. Atomic clocks and natural reactors and ancient rocks place stringent limits on such variations, and so far they suggest remarkable stability. Finally, we can assess anthropic reasoning by its rare, coarse predictions, like the one that anticipated a small positive vacuum energy balancing their successes against the unease they provoke. While we probe, we should guard against several intellectual traps. The first is the puddle fallacy, the temptation to marvel that the universe fits us so well, forgetting that we fit it because we are its product. This does not dissolve the fine-tuning question, but it reminds us not to overinterpret coincidence. The second is the inverse trap, dismissing fine-tuning as mere illusion because probabilities over unknown ensembles are ill-defined. Even without a well-posed probability space, the explanatory demand remains. Why are the parameters compatible with complexity at all? The third trap is overconfidence about necessity. History has humbled us many times. Yesterday's must be has often become today's. It could have been otherwise. Perhaps a future theory will show that some constants could never have been different. But until it arrives, humility is warranted. Let's descend from the abstract to the tangible and watch fine-tuning at work in the places we can picture. In a newborn star, balance is everything. Gravity pulls inward. Plasma pressure pushes outward, and the rate of nuclear fusion in the core mediates the truce. If the weak interaction were far stronger, the proton-proton chain would run too quickly. Stars would live fast and die young, scattering heavy elements before biology could take its time. If far weaker, the chain would stall. Stars would struggle to ignite, leaving the universe cold and dark. The abundances of carbon and oxygen, critical to organic chemistry and water, depend on a gentle conspiracy between nuclear forces and electromagnetic couplings. A slight shift in the quark masses or in the strength of the strong force moves nuclear energy levels, and with them, the branch points in stellar alchemy. Planets inherit the output. On worlds where carbon is scarce or oxygen is rare, life as we know it faces an uphill battle. Meanwhile, gravity's feebleness, so puzzling to theorists, turns out to be a gift to time. Because gravity is weak, stars can be enormous and long-lived. Small changes to this balance compress cosmic history or stretch it to lifeless thinness. Not every dial matters equally for every outcome, but the orchestra must play in tune for complex, evolving chemistry to take the stage.
Some of the eeriest fine-tunings hide in initial conditions. The early universe's low entropy is a case in point. Entropy counts the number of ways a system can arrange itself while looking macroscopically the same. On that measure, a smooth, nearly featureless universe is exquisitely special, like a deck of cards that emerges perfectly sorted after 1,000 shuffles. Why did our beginning wear such improbable order? One proposal is that cosmic inflation, an early burst of accelerated expansion, stretched space smooth, ironing out wrinkles and explaining why distant regions look similar. Inflation also seeds the density ripples that grow into structure. Yet inflation itself may require its own special initial state to begin. And in some versions it never truly ends, spawning a vast fractal of bubble domains, the multiverse again, knocking at the door. We find ourselves turning in circles, as if the answers prefer to come in pairs. A solution that tames, one fine-tuning, sometimes opens a window to another.
Even if multiplicity is real, it does not automatically dispense wisdom. If there are countless domains, we still need a way to say which ones are typical and which rare. This is the measure problem. How to weigh infinities without cheating. Depending on the rule you choose, the most probable observations can change wildly. Does your measure count observers, galaxies, or volumes of space? Do you slice time by constant expansion rate, by temperature, by something else? Different choices yield different expectations, leading to paradoxes and debates. It is a humbling reminder. Probability in cosmology is not the same as rolling dice in a casino we built ourselves. Where does this leave the idea that a final theory fixes the constants? Not dead, only demanding. Some physicists hold out hope that deep symmetries or consistency constraints will eventually pin down the values we measure. Others look to information theory and computation. Perhaps the laws we see are those that maximize the computational capacity of the universe, or those that minimize algorithmic complexity while permitting rich structures to emerge. At the speculative edge, proposals like the universe is a mathematical structure recast existence as the set of all consistent mathematics. Our world is simply one such structure that contains self-aware substructures able to ask questions. These ideas are thrilling or frustrating depending on your temperament. They shift the burden from physics to philosophy, though some argue that, in the end, the two are not so easily separated. What about design? It would be unfair to pretend that scientific curiosity exists in a vacuum untouched by human longing. The sense that the cosmos is balanced just so has often inspired spiritual or teleological interpretations. From within science, we cannot adjudicate purpose. We can only insist on coherence with observation. If someone claims that fine-tuning is evidence of design, that is an inference about metaphysical causes from physical data. It may be personally meaningful. It is not within physics testable without additional commitments. The most we can say is that fine-tuning is compatible with purpose, just as it is compatible with multiplicity or inevitability. Whether one finds any of those satisfying is a matter of taste argument, in the slow accretion of new facts.
For the simulation hypothesis, the route to evidence is, in principle, clearer. If we are emulated on an underlying computational substrate, perhaps there are bugs, shortcuts, or discretization artifacts we could see, limits to the highest energies, preferred frames, small violations that betray the grid. High-precision experiments have searched for many such anomalies and continue to press the bounds. So far, the world behaves as if its underlying rules are continuous and symmetries exact to the limits we can probe. Could a superior simulator hide all traces? Of course. But then the simulation becomes, in practice, not distinguishable from reality, a philosophical flourish rather than a scientific engine.
There's another posture we can take toward fine-tuning: gratitude without surrender. We can acknowledge the strangeness of the numbers while refusing to leap to closure. We can let the question enlarge our sense of wonder. For all its severity, physics is generous with wonder. It gives us a universe in which hydrogen, the simplest atom, has just the right spectrum to form molecules and clouds, in which stars burn for billions of years, in which black holes punctuate space like punctuation marks in a cosmic sentence, in which the quantum undercurrent is wild yet, on average, obedient. It gives us a universe where the laws do not change capriciously from place to place, and where the same mathematics that describes the electron in a lab also describes the chemistry of a distant nebula. That unity is a kind of tuning, too, not just the values of numbers, but the very existence of universal, comprehensible laws. As we reflect, it helps to remember how far we've already come. A century ago, the idea that the universe had an origin was controversial. A few decades ago, dark energy was science fiction. Today, we map the large-scale structure of galaxies as if charting a new continent, weigh the cosmos' components with percent-level precision, and measure time with clocks that will be off by less than a second over the age of the universe. We will not stop. Future observatories will sharpen our picture of the cosmic microwave background in the distribution of matter. Particle colliders and precision experiments will chase new symmetries and test whether naturalness was the right compass or a false north. Gravitational wave telescopes will hear black holes and neutron stars collide, perhaps revealing clues about matter at densities we can only imagine. And somewhere in that unfolding data, patterns may emerge. Patterns that either make fine-tuning look inevitable or drive us toward a multiverse or something stranger still. There's a quiet human dimension to this story. Fine-tuning tempts us to read the universe as a mirror. Some see confirmation of meaning, others see an invitation to humility. After all, a life-friendly cosmos is not a person-friendly cosmos. It is vast, cold, and mostly empty. It permits life. It does not pamper it. The same equations that allow stars to warm planets also build supernovae that sterilize them. Our presence is possible because the dials are set within narrow ranges, but the universe does not lean down to whisper why. That silence is difficult and beautiful at once. It leaves room for gratitude without certainty. It leaves room for science to keep asking and for philosophy to keep listening. So here's where we stand. We have a puzzle dressed up as a cosmos. Its solution could be inevitability, a final theory with no wiggle room. It could be multiplicity, a landscape where life surveys its habitable oases. It could be an emergent principle we have not yet glimpsed, where the laws are the byproduct of deeper informational rules. It could be purpose, simulation, or something we haven't yet named. The right answer might be a mosaic, a multiverse populated by vacua, governed by a deeper mathematical skeleton that restricts possibilities, while observers arise only where the constants fall into place. All of these are live options, ranked and argued over by thoughtful people who are doing their best to let evidence lead and metaphors follow. When you strip it down, fine-tuning is a charge to curiosity. It says, do not be fooled by familiarity. The universe did not have to be this way. It could have refused to write stars into its script. It could have denied atoms their stability. It could have left the stage dark and the audience empty. It did not. We live in the afterglow of an improbable permission slip. That should make us rigorous, not credulous, patient, not complacent. The work of understanding is long and communal. It asks for clear thinking, for restraint with big claims, and for a willingness to revise our expectations when nature shrugs at our favorite ideas. As our story winds back to the beginning, return to that image of the cosmic mixing board. Somewhere in the deep structure of reality, whether in a single studio or a vast warehouse of rooms, there are sliders. They have labels we partially understand and values we measure with care. They are not ours to change, but they are ours to contemplate. Perhaps one day we will discover that they could never have been otherwise. Perhaps we will discover that they vary beyond our horizon, that their placement here is an accident of cosmic geography. Either way, the act of listening has value. The symphony playing through those settings is the only one we know. And for now, we are among its briefest, luckiest notes. We began with a promise to follow a question to its edge. We have walked past stars and symmetries, through probabilistic thickets and philosophical clearings, and we have not reached a verdict. And that is fine. Some mysteries are honest invitations to keep traveling. So I'll leave you with the question that echoes whenever we look up and count the improbable blessings of our physics. If you had the power to nudge a single cosmic dial, would you dare? Or is the greater wonder that they were set at all? Tell me what you think in the comments. Because this is one of those puzzles the universe asks all of us, together.